So experimental design actually refers to a set of practices, but specifically, we're going to be looking at what is an experiment. And in statistics, this has a very precise definition and is not to be confused with observational studies. The difference is, with an observational study, there is no random assignment of groups. So you are not interfering with the variables themselves. You are just watching, observing your subjects and collecting data from them passively. Whereas with an experiment, you are randomly assigning groups. Specifically, for an experiment, we have a set of groups called the experimental or treatment group, and the control group. The reason for having at least these two groups is that if you want to measure a response in the response variable, you need to compare it to a baseline. So here's a good example for separating in an experiment into experimental and control groups. So suppose you're testing a new treatment, like a medical treatment, okay? And you have a group of people that are willing to participate in your study. All of them need it. So all of them need this treatment. But some of them will get this treatment. So it could come in the form of a pill or an injection. And some will not. And the way that you assign people to each group is randomly using a cluster sampling process. Right? So some of them go to this group, some of them go to this group. Now, there is an effect that needs to be considered, which is the placebo effect, where sometimes someone receives a not treatment, but they think it is a treatment. And a way to prevent this effect, so non-treatment subject behaves as if they did receive the treatment. And it's actually a well-known effect. And it is real. It is not just, psychological. One way to prevent this effect from derailing your experiment is to initiate blinding. So here's the idea. When you're sorting between your treatment and your control group, right? If this treatment is maybe a pill that has the medicine, the others may get a sugar pill. But they won't know which one's which, so you make them identical. That is blinding. But we can also do double blinding. Where not only do the people in the groups themselves not know which one they're getting, but the experimenters also don't know. So they split them into the two groups, and then the experimenters are giving out identical pills that are not distinguishable to them. There's another group later on that does receive the information about which group is which, and then eventually everyone gets in on which one was which. There is an ethical consideration here, which is if this is a treatment that is for a condition that's potentially life-threatening, what are the ethical considerations between letting some people in your study not get the treatment that could save their lives? This came up during the vaccine trials for COVID-19, specifically the Moderna vaccine, where one of the ways to deal with that ethical issue is to let the control group eventually get the vaccine as well after blinding. So when you blind, you can afterwards you unblind. And this is true for blinding and double blinding. So eventually everyone knows which group they're in, the people in the experiment and the people not doing the experiment. And when you unblind, then people will know that some did not receive the treatment, and then they can then get the treatment if it's shown to be effective. So all this is to say that if you want to measure an effect from an explanatory variable to a response variable, then you need to set up a control and treatment group to account for differences in the explanatory variable and therefore measuring the response accurately. How to actually do this? There's a couple of different ways. So when you randomly assign, we talked about how you can use cluster sampling to create your control and your treatment group, but you might want to do better, right? So just for the sake of illustration, think of your your sample for your clinical study or whatever kind of experiment and let's say there's 100 people. So one way to do this, right, we already talked about it, is to do cluster sampling. So 50 of them get randomly assigned into the control group, and 50 of them get randomly assigned to the treatment group. And this is what we call completely randomized design. There's another way, because if you'll notice, this is completely random, so any of the confounding variables, we're not really accounting for those. If we want to account for confounding variables, on the other hand, then we can use what's called a randomized block design. And here's how it works. Instead of doing cluster sampling, what we'll do is we'll first stratify our sample into blocks. So essentially, this is a stratified sampling method where we stratify along some criteria that's important in order to avoid confounding. So for instance, if this is a treatment for a vaccine, maybe you want to avoid age factors. And so you partition your group into, let's say, and one of them are, so 30 of them are under the age of, so young adults, and then some of them are middle-aged, and some of them are elderly. And then just depends on how many exactly you have. So for the sake of simplicity, let's say the breakdown is 30, 30, 40, right? From these, now you split each one into a control and treatment group, right? So for young adults, YA, not to be confused with the genre of literature, you now have your 30, half of them get split into your control group and half of them into treatment group. So control group, treatment. So let's call that K1 equals 15, K2 equals 15. But they add up to the 30, right? And then you do the same thing with your, sorry, that's not the right color. You do the same thing with your middle-aged adults. There's a control group. and a treatment group. And again, you split them in half. So now in this process, you're doing the cluster sampling. Right. So again, there's 15 here, 15 here. And among the elderly, well, there was 40 of them to begin with. So your control group and your treatment group, now you have 20 in one and 20 in the other. So it's stratified, and then you perform your cluster sampling within each subgroup. And this experimental design is called randomized block design. And you can do this for as many confounding variables as you want. We did it once for age, but you can also use it for if you wanted to account for gender effects or underlying conditions. You could do it again and again, which makes it more complicated, of course, but now you have accounted for all those different effects.